Well, hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you today as it is every day here in my virtual classroom. If you step on inside, we are looking at section 8.2 in the Big Ideas Math Integrated Math book textbook on similarity and transformations, which actually kind of surprised me, and I apologize. In my 8.1 video I said that was a precursor on dilations to everything else that would be similarity hereafter. And I should have looked harder at that second word on here. It's similarity and transformations, which I suppose is supposed to talk about dilations once again, a little bit more so. So, more back on the dilations front. We'll see what they actually have to talk about. I am aware that it looks like dilations are still a part of what we do with some graphs. So strap on in, buckle up, and we'll take a look. And I still promise you that similarity goes beyond what we do on graphs. But it's going to have to do with some proportion things and some proofs probably here and there. So we'll see what this one all has to do with, though. Let's go ahead and take a look right now. We are going to, let me turn down my volume. Perform similarity transformations, describe similarity transformations, and prove that figures are similar. Interesting where they say prove that figures are similar, because we're going to be doing that more. There are sections dedicated to that for triangles. This one's not in triangles, and I'm curious to see what they actually do with it. I'm trying to figure out where I should move myself. Core vocabulary, similarity transformation, and similar figures. So, it's important I start saying that word now because I used the word in 8.1 a lot, but they never did, right? They only talked about dilations. I used the word similar, so now they're going to describe or define true similarity to you. If you heard my 8.1 video enough, you might know what it is now. You might have an idea. But let's see what they say. A dilation is a transformation that preserves shape but not size. So a dilation is a non-rigid motion. Let me just look at those two sentences once again. Preserves shape but not size. So something's still a triangle, but really more so a right triangle or also an isosceles triangle or whatever. It's still the exact same thing that it was. It's just a bigger version of it in all dimensions. And if we're talking two dimensions, both this way and that way, it grows in size outward or shrinks, but it maintains those angle measures to be the same, things like that. Since the dilation is a non-rigid motion, you've heard of translations, reflections, and rotations. Those are rigid motions. They keep your figures congruent. Dilations are not congruent. Transformations are they do not provide congruent new images. They provide similar images. A similarity transformation is a dilation or a composition of rigid motions and dilations. So dilations need to be had. Two geometric figures are similar figures if and only if there is a similarity transformation that maps one of the figures onto the other. Similar figures have the same shape but not necessarily the same size. So the big thing here is think the angle measures need to be the same. Think it just needs to be a bigger version of the object. Congruence transformations preserve length and angle measure when the scale factor of the dilations is not equal to 1 or negative 1. Similarity transformations preserve angle measure only. So if you had a scale factor of 1 on something, that means that its size didn't change, neither did its shape. And same with negative 1. It might have changed its place in space, and I considered that a 180 degree rotation, but it's still a rigid motion. Once it turns into 2 or negative 0.5 or 17, something like that, suddenly it would be different. So if you get some dilations involved, you have similarity of figures. Performing similarity transformation. Graph triangle ABC with vertices here and its image after the similarity transformation. So here they're going to give you rules. And I just said this is one of the transformation rules, a translation, where you move objects. I'm not going to talk a long time teaching this. I'm just going to show you what they do. They take your x's and y's, they take your x's and add 5 to them. They take your y's and add 1 to them. It's another way of saying go right 5 units and go up 1 unit. So from ABC to A prime, B prime, C prime, the red triangle, notice how like A went 1, 2, 3, 4, 5 units to the right and 1 unit up. And you can mathematically do this, by the way, but this is also a count, right? So if A was at negative 4 plus 5 is 1, things like that. And then it went 1 up because the Y plus 1 plus 1 is 2. Same with B, same with C, you connect them, you graph them. So you go by the rule described here, and it's a translation. A dilation, we've seen this before, or at least the idea of it, where we multiply, we double our x's, double our y's, but that was after the translation. So the translation happens first, boom, boom, and then the dilation. Something that they might ask a question on is, would you do the same thing if you dilated first and then translated second? Would you end up in the same place? If that answer is no. That's probably something that they might tell you or ask about later. At least not for those ones. Step 2, step 3. Okay, so they're just saying what you did after that. Okay, there's an example. Let's keep seeing. So we're going to do some of those as well. Describing a similarity transformation. Let's describe a transformation that maps trapezoid PQRS to trapezoid WXYZ. So you want to find a way to make it not only be smaller, but also face this direction where it goes over. This is where a reflection is a good one that we'll talk about. And like I said, these other transformations you would have done in IM1. So again, I'm not going to spend a long time teaching them. I'll do them as I go, but this is going to be more about dilations and obviously answering the questions. So the first one they talk about here, well, I don't know which one. Okay, they do the reflection first. So the first thing they do is they reflect over the y-axis right here. It's also across the line x equals 0. You'll notice you get a mirror image that's in red. That's what it's called, a reflection in the y-axis. We should know that actually from IM2 stuff. We did this when graphing parabolas, reflecting in the x-axis at least. So reflecting the y-axis, graph flips over. Now we got to dilate it. And what you'll notice is what the points become. So you're from Q. Oh, they had to change the point names. Q prime seems to correspond with X because where the angle measures are the same, things like that. So you see that Q goes from 3, 3 and X goes to 1, 1. What makes it go from 3, 3 to 1, 1? Well, everything got divided by 3. And remember, both have to do that, divided by 3, but that is also multiplied by 1/3. So they got multiplied by 1/3, and you can see everything else follows suit. They all have to. If they don't, it's not a dilation, right? They all have to follow the exact same rule, which means that their center is their center of dilation is the origin. That's also something else. I do wonder if they're going to give us centers that are not the origin, and you'll see once again that you should be able to draw straight lines out to these points for things that are corresponding. Those aren't technically straight, but you know what I mean. So they should all find a center. So we'll find a center even if it's not the origin in some other cases. Here's another one. This one actually involves what looks like a rotation. I'm not going to do the whole thing, but you can see that F goes to U. So there you go. But you can see it's some sort of rotation, 180 degrees. Once again, one of those things that makes more sense if you've done them before. But that's part of what we talk about. It's probably good that we draw the other points that go alongside them when we do them. Proving figures are similar. Again, kind of interesting because we'll do it with triangles in future sections. But to prove figures are similar, you must prove a similarity transformation maps one of the figures onto the other. Okay, so it sounds like we're doing the transformations but not on graphs. Given square ABCD with side length R and square EFGH with side length S, and these two are parallel, AD and EH, prove that these two squares are similar. Now they tell you they're squares, which is probably important. Let's see what they say, because I don't know how I want to answer this best. That's a lot. Let's see what they say. They translate, literally, these are actually different places in space, so they actually have to have you map one onto the other, literally. They're saying take this object and move it to the right over here, so now it's right there on it. Translate square ABCD, what did I just do? Translate square ABCD so that point A maps to point E. So they put A on E right there. E and A, EA are right together right there. So they move it right into that. Because translations map segments to parallel segments, and AD is parallel to EH, the image of AD lies on EH. Okay, that would be a lot for me to say, I'll be honest. I don't know if I'm going to be very comfortable in saying all that stuff out loud, but I might move objects with you. So I apologize if I'm not very descriptive when answering questions like this. Because translations preserve length and angle measure, the image of ABCD, E, B prime, C prime, D prime, is a square with side length R. Because all the interior angles of a square are right angle, all these angles are the same. When ray ED coincides with ray EH, I'm not going to be able to answer these questions, guys. I hope they don't have too many of these. Ray EB coincides with ray EF. Okay, so now these ones are in coincidence because those other two are in coincidence as they're squares. So this lies on EF. Next, we can dilate the square using center of dilation E. That makes sense. This is now your center, and we expand from there. Everything's growing out from that direction, like outward. Boom. Almost like it was the origin. choose the scale factor to be the ratio of side length S over R. So remember, scale factor, we divide the image by the pre-image, if you will, things to figure out what you have to multiply R by to get S. So it's S over R. If this was 10 and this is 5, then 10 over 5 is 2. Things like that. There's more. This dilation maps ED prime to EH once you dilate it. Because they have side length S over R times R, which is S. Okay. And segments ED on lines passing through the center dilation. The segments ED prime and EB prime line, the lines passing through the center. Sorry. So the dilation maps B prime to F and D prime to H. The image of C prime lies this many units to the right and this many units up. So it hits to G. C prime is G. A similarity transformation maps those two. Wow. I'm not going to be able to do all that. I'll be honest. I'll say things out loud, and hopefully we can make sense of that. I'm not going to be typing all that. I'll be upfront. That's going to be a lot. Otherwise, I'll be going back and forth with it. But that is the last kind of example that we have before we just go ahead and take a look at the vocabulary and core concept check. Then we'll do all the other stuff. What is the difference between similar figures and congruent figures? So, yeah, this really needs to be answered pretty well here. Congruent figures are identical in size and shape, whereas similar figures are only identical in size, not shape. Or shape, not size. Only identical in shape, but not size. So they preserve the angle measures, but then there's a similarity ratio, or there's a scale factor that gets attached to the whole thing. A transformation that produces a similar figure, such as a dilation, is called a similarity transformation. There's not much room for me to put this, but similarity transformation. And it's a non-rigid transformation, I believe we'd call it. So there it is. All right, those are the first two there, guys. So let's go ahead and get started. Now, this is a much shorter problem set, which is my validation for being able to do this tonight. Trust me, I've had a long couple days, and I just got home from that one. So I'm glad that this is short. Did she homer? I think she homered. So I hope it's short enough, at least for myself, because I'm going to need it. I need some of this. All right, guys, let's go ahead and take a look at what we got here. Now, it's best that you know some of the IM1 stuff when it comes to, I'm copying a graph, looks like we got to use them. When it comes to translations, reflections, and rotations, and it's also probably best that you got my 8.1 stuff down. Not necessarily mine, but you got 8.1 stuff down, and refer to that video if you need it for this stuff. Next stuff. All right, next exercises 3 through 6. We are going to graph triangle FGH with those vertices, and then we're going to do the following transformation. So at least we get to practice these ones, all of translations, reflections, and rotations alongside these dilations with the rules. So let's start with F at -2, 2, G at -2, -4, and H at -4, -4. So F, G, H, and let's apply some transformations, shall we? Let me connect these. Sorry, give me a second. Of course, this thing will snap everything out of focus. Okay, let's begin with translation. I'll put it down here. From xy to x plus 3, y plus 1, and let's color code this actually. I'll put this in green, and then that will be in green itself. So this means let's go 3 right and 1 up for every point. 1, 2, 3 to the right, 1 up. That'll be G prime. F prime also gets to go 1, 2, 3 to the right and 1 up, and so does H. Now, if you want to, because this is a rigid motion, H will still be 1, 2, 3 to the left of G, so I could also go 1, 2, 3 to the left like that, and that actually works out just fine. And you do want to draw this one, even though there's something else you're going to do after, because you don't want to lose what you do next. Next, what I'm going to do in my dilation is take what I have in green, not in blue, but take what I have in green to apply the next transformation. So let's do that in one purple. Let's do a dilation after that. I guess this won't be very short, because I'm going pretty much as fast as I can while copying down the problem. From xy to 2x and 2y. So now we have a scale factor of 2 applied. This is growing from the origin. So from the origin, we do have this f prime at 1, 3. Doubling that will be 2, 6. So 2, 6 here is our f double prime. Doesn't look like they give us new letters. G double prime will be at 2, negative 6. Now, technically, this distance will get doubled. I can go 1, 2, 3, 4, 5, 6 like that, h double prime, and all will be taken care of. And if you look at that, negative 2, negative 3 doubles to become negative 4, negative 6. So that actually worked out the same way that I showed in that other thing, that you can also apply it that way. And here's the final result that we have on that guy here. And that's what we got. So the purple is the answer. That's the new full image after the composition of transformations for number 3. All right, let's go to number 4. Number 4, we begin with a dilation and then we do a reflection. Now, I did mention that in some cases these things are not like doing dilation first, reflection second, etc. You can't rely on them getting you in the same place. So make sure you do follow the order in which they're written. Let's begin with, let me just copy and paste the FGH. I didn't notice it was the same set. So I don't know if there's an easy way. You know what? I'll do it this one more time, and then just copy this whole thing. I didn't realize it was the same set. That makes one part a little bit easier for me. What was it? Negative 5, negative 4. So FGH. Let's make this one look pretty because I got to do it for the next 2 problems. That is purple. But yeah, if I did the dilation first and the translation second, I wouldn't have been in the same place for that last problem. So just kind of keep that in mind. Kind of definitely keep that in mind. All right, let's just group her up. That's fine. All right, keeping that ready for the next thing. So first one we're going to do is the dilation. We are going to halve our values, divide them by 2. Now, we know what the numbers are from the ordered pairs, so, and that means they're going toward the origin. From negative 2, 2 to negative 1, 1 will be f prime. That is half the distance, half the x, half the y. From negative 2, negative 4 to negative 1, negative 2. And I keep mentioning this, and I'll do it once again. Half of 3 is 1.5, 1.5. And so this is where h prime is going to be. Now, I did that without finding out what half of h's ordered pairs were, but everything works in the same way. It's not just half the distance toward the center of dilation, it's also half the length of the object itself. So it works both ways. And anytime I can do that, I think I'm going to try and do that with you guys. So reflection in the y-axis. So the y-axis, the axis of symmetry that we have right there, and I want to draw it as well, is right here. That's the y-axis. We're going to reflect across the y-axis from the green object here. F prime goes over here. And what I'm doing is I'm going perpendicularly across a vertical line, so I'm going horizontally. I'm staying the same distance away. 1 away, 1 away. This thing mirrors over. It's going to be a reflection. G prime is also 1 away like that. And once more, H prime as a reflection, instead of being to the left of G, will now be to the right of G. So we'll be 1.5 away over here, which is also, 1, 2.5 away from the axis of symmetry. So here's my F double prime, G double prime, H double prime triangle after the 2 transformations that were applied. I think those are 2 different purple colors I have marked there. But that would be the final after all said and done for that problem. Number 5. By the way, I do believe that doing the reflection first and dilation second for that problem would have given you the same answer, if that matters. Because it was all multiplication of some sort, even if it was multiplication by negatives. When it's addition with multiplication, Order matters. All right, number 5, let's begin with rotation. Rotations are hardest to really talk about, but we'll do what we can. 90 degrees about the origin. That means the origin is basically my center. Basic way I'm going to put it is this, and I'm going to... Oh, they didn't mention, by the way, direction. If I recall, the default direction of rotation is counterclockwise. If they don't tell you the direction, assume counterclockwise. So imagine this kind of rotation like that. Now, you're not rotating the graph itself, you're rotating the triangle. But here's where I'm going to place my triangle eventually. Look at this triangle here. Don't look at where the axes move. Just, in fact, close your eyes for a second. Close your eyes. Are you closing them? Close them now. Keep them closed, and open your eyes. Okay, so imagine that those axes never moved, but look at where this triangle is. This is where I'm going to draw my next triangle. Not from here, I'm going to draw it there. Boom, 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 boom. Now, the blue triangle will still be here, but this is a 90-degree rotation. Every point went that way. So, and it's about the origin, which means they stay the same distance away. So F was at -2, 2. F prime will be now here at -2, -2. And this is the toughest for people to use. If you're doing this, you can rotate your paper 90 degrees counterclockwise, and you can look at where it looks like it's going to be by ordered pair. So once again, if I did another rotation of this, and I'll bring it back, but if I rotated this here, look at G now at 4, -2. That's where we're going to be putting G prime at 4, -2. And again, I don't want to teach this. This is something from IM1. H, hey, if it helps, before it was to the left, what happens after you rotate 90 degrees counterclockwise? Now it goes downward. So H prime, 1, 2, 3 units downward like that. And this is a 90-degree rotation counterclockwise about the origin. The origin 0, 0, which just means stays the same distance. And that's best that they probably do that for these problems. Not have a different center. And if they do, we'll have to play with it. It'll be a little tough. There's the rotation. This thing swung that way. Okay, now we do a dilation where we triple everything. And as you can imagine, well, you might go a little bit off the map here, and I'm just going to deal with it. Dilation. I can write the points if you want to, but we're going from xy to 3x, 3y. So check this out. We went from an f prime of -2, -2 to an f double prime of triple those, -6, -6. So we're now going to be right here. Remember, we're taking it from the green, f double prime. G prime is at 4, -2, and we triple those to get 12, -6. So a little off the map. Just pretend like we got here 12, -6. So there's your G double prime. Hey, if you want H double prime, we got a triple 3, right? That'll be 9 down from there, but it's going to be out there. So 9 down from -6 is actually -15. So, you know, that's where that's going to be. H prime is at 4, -5. And so H double prime is at, 12, -15. So, you know, yeah. Right? Do what you can. I'm just using this version of this graph paper. Sorry. I don't always anticipate for a problem like this, especially since 2 transformations occur. It's kind of harder to mention. But the rotation happened first, and then this thing dilated, became 3 times its size. All right, number 6. Dilation, then a reflection. Now, 3/4. As long as, well, these numbers might not be great, just so you're aware. So number 6, let's begin with a dilation of 3/4 what they were before. So from whatever the XY values were. And the only other problem is not just the dilation here, but also the fact that we have to reflect after. Things are going to kind of get in the way. What's 3/4 of 2, right? It might help to write these. F was at -2, 2, and F prime. What's 3/4 of 2? 3/4 of 2, 2/4 is 1/2. So that's 3/2. So -3/2 3 halves. That's negative 1.5 comma 3 halves. So negative 1.5 comma 1.5 like that. That's your f prime, right? That's what we're doing. Now g was at negative 2, negative 4. And then we already know what this first one's going to be, negative 3 halves. And this is negative 3. 3/4 of negative 4 is negative 3. So now we're going to be right there. What's 3/4 of 3? 9/4. This is going to be a little tougher to kind of bring up, but let's just do it. Negative 5, negative 4. Of course, they like to do this. So h, whoops. Let me try that again. H prime. 3/4 of 5 is 15/4. 15/4 is 3 3/4. So we're going to be at negative 3 3/4, negative 15/4. And then that negative 4 goes to negative 3. That's going to be the same height. So negative 3 3/4. 1, 2, 3 3/4 like that. There's your h prime. And remember, we should be able to draw a straight line from here to the origin, you know, like that. So I should probably move this over just a little tick like that. Close enough, I guess, for me. Okay, so that is the new triangle of 3/4 its previous size. I didn't see any negatives here yet. This is the last one, at least we see. That's the dilation. We still have the reflection in the x-axis. So x-axis, not the y-axis, is the horizontal line in x-axis. This is the x-axis here. So now we're going to traverse across this thing like vertically. F prime is 1.5 units away vertically. So now we go down 1.5 units over here for F double prime. Like I said, there's going to be some overlap here. It's going to get a little cluttered. G prime is 3 away, so this will also be 3 away. At least these aren't too bad. G double prime and H double prime 1, 2, 3 away, 1, 2, 3 away there as well. Gets very cluttered with that involved. But it's a part of it. And there's the graph. So we got all the graphs in. Very strange. The purple's the final. There you have it. Okay, there are the first 4 problems. Maybe this will go a little longer than I expected. In exercises 7 and 8, describe a similarity transformation that maps the blue pre-image to the green image. Okay, there are a lot of ways you can do these problems, keeping in mind that dilations do have a center and they grow in they follow the same rule, growing every which way in a direction. I really recommend you find that center first, though. Here's what I'm going to do to find the center. And I don't know, because they didn't talk about doing problems like this. First of all, make sure that things correspond the way they're supposed to, as in they're oriented the same direction. Clearly, E goes with U. Looks like V with F and D with T, right? Let's draw, we did this with compass construction in 8.1. Let's draw straight lines through corresponding parts like this and this, T through D. And you can see this point of concurrency if you're watching. This is not the origin. This point of concurrency, this center of dilation where these things are growing from, is not the origin. It is at 0, -1. So the very first thing I want to make mention of, and by the way, it doesn't look like there's a translation of any sort. Maybe I lucked out with that. But these are the only 2 sets of points that we have. It just says from the blue to the green. And blue to green, by the way, is an enlargement. There's only one transformation here that's a dilation. We'll begin with that. Dilation from center 0, -1. That's the first thing I'm going to bring up. What else do we have to bring up? Next thing we have to bring up is scale factor. Now, the problem that becomes tricky here is you wouldn't really want to think of ordered pairs anymore, as in E is at 1, -2, and U is at 2, -3, because it's not going from the origin that these numbers are doing this. You got to look a little more so at how those directions go. If I talked like slope from this center, E is down 1 over 1, and U is down 2 over 2, that's a good way of almost saying that E is like a de facto 1, -1, and U is like a 2, -2, kind of like that. It's a new form of them. That's not their real points, but they might as well be when it comes to comparison. What happens is we go from these X's and Y's to doubling them. They become double what they were before. That means your scale factor is 2 with the scale factor of 2. And this is one way that you can do this. That also means this was n enlargement. This was n enlargement. So that can be my answer right there. Now, another thing I could have done, which that was a pretty good approach. Another thing you could have done is, remember, you can compare lengths. It's not just distance from the center. It should also accompany overall lengths. From F to E is a length of 2, and from V to U, the corresponding side length is a length of 4. 4 divided by 2 is 2. Remember, it is an enlargement. From U to T, this length is 8. From D to E, this length is 4. 8 divided by 4 is also 2. So the scale factor is clearly 2 with this scenario here. A lot of ways you can play with that, and honestly, the book didn't really tell you about any of it, so that's why I'm here to tell you about it. So that's what I'm seeing, and that's what I'm saying. Number 8's a little trickier, and more so, I'm going to copy and paste it because I like to map. It's going to take more than one thing. A dilation is involved, but there's also clearly something else going on. Now, to me, it appears to be a reflection that is also going on. Let's just play with this on top, and then I'll write an answer down below. So, whoops. So, we're going from blue to green. So the blue's the bigger one, right? Let's actually start. This sounds counterproductive. I'm only saying this because of the room we have, which is very little. Let's maybe start with a dilation. Even though we don't have it mapped right. You can probably tell L goes to R, right? P goes to J, things like that. But let's shrink it. If you imagine that this thing will do kind of what you want it to, by shrinking it, we also need to find a center. This is where I can't really draw a line yet, unless there were things that we knew where the center came from. So that's an unfortunate part here, but I think they're not going to make this too tricky. My guess is the center is the origin. And if I shrink this through a dilation, let's call it L prime. Looks like if I go half, and I don't know how to answer how I'm doing this, I'll be honest. I don't know how to answer how I'm doing this other than just to know that I'm doing it, which is why I'm saying a reflection may be better first. It's just they didn't give me graphing room. Okay, you know what? I'm going to do the reflection first. It's not going to be in proper graphing room. What you can tell is this thing needs to flip over this way. Whoop, and flip over that way, things like that. This thing needs to go over what looks like the y-axis. If I reflect over the y-axis here, L prime will go over here. Okay, I don't think you'd understand this until I do this reflection. M actually stays where it is. M prime and M are in the same place because they're in the same place. They're on the axis of symmetry. Here's the problem. J prime will be 6 away over here, and it doesn't really fit. 5, 6, I'm just making it up, but it's about right there. And K prime's the same thing. It'll actually be 4 up from there, but again, 6 away. So they weren't very kind in not giving you that stuff. I assume you get to graph this yourself. I guess that's another reason why we should just do it this way anyway. So let me draw that in purple here. This began with the reflection in the y-axis. How can I tell? Well, you can tell by the way that it orients, and I don't think we're talking about reflecting across any different lines yet. And if we were, we could do a translation with that afterward. I don't think we're going to need that translation, though. So the first thing I want to say is reflection in the y-axis. Reflection in the y. Reflection in the y-axis. Okay, that's the first part. And then what? Here's the dilation part. Now we can actually draw lines to parts that would correspond. L prime goes with R. Let's see if I can thin this out a little bit here. L prime goes through R and to where? J with, no, excuse me. J is not a part of it. J prime with P to where? K prime with Q to where? And M with M really to nowhere, but because it's on that line, I guess we can just draw it straight down. You can see they're all going to the origin. They're all going to the origin right there. So that's the center of dilation. Looks like we're going half the distance from before, right? This whole length was 6, now it's 3, things like that. And everything's shrinking half the size that it was before. And I know it's a very cluttered drawing, but we go one part at a time. So reflection in the y-axis and dilate with center is center origin, center 0, 0. I don't know how they say it. By scale factor of 1/2. Now that it's a reduction. Okay, that's number 8. Let's move forward. Yeah, you know what? This actually goes pretty slowly. No wonder why they have 22 questions. Numbers 9 through 12. Determine whether the polygons with the given vertices are similar. Use transformations to explain your reasoning. So let me copy and paste another graph thing. Of course, they won't fit these within the window range always. Looks like the first one already has a culprit of this. So I'll just plot them. So A, B, C, which is off, but we'll check it out. A, B, C. Yeah, this is kind of a weird section to teach. You know, it's going to be a little weird. It's weird to talk about because there's a little bit of intuition. Seeing an image for what it is, that part's clear, but the order in which I'm doing it, reverting back to some of the previous transformations, depends on how easy they make it, because they could make them hard, obviously. D, E, and F. D, E, F. Okay, well, there's one thing that we can see for certain, and it's part of that intuition, which is if there's a semblance of similarity, which parts would correspond. Now, I think they were also helpful with letter order. A is with D, E is with B, and C is with F. And they're oriented the same direction, right? Clear as day. That will help you out. Now, the next part is you can choose to go with which order you want to do this. But because it seems like there's no reflection or rotation, that translations are possibly a part of it. I mean, there's more than one answer, by the way. It says use transformations to explain your reasoning, but there's potentially more than one answer. If I wanted to say it's a dilation right off the bat, I could, in the way that I could say draw A through D, draw B through E, draw C through F, and where do we end up as a center, right? And then like, boom, it's at some random spot right there, and I don't really know what it was. But if we get a translation involved to begin with, I think that'll help much more. So this one, I don't know if I can really pick it up and move it because they're all individual object things for me. I'll kind of pretend like I'm doing it. I could translate this whole thing to like here, and I do it specifically to here to map, well, actually I'd probably do it here. I'd probably move it up here so that I could shrink it all in toward this as my center. So I can translate it 6 units left, 3 units up. And then I can shrink it if it has a proper dilation. And I think I kind of want to do that. So let me just imagine I copy paste and change it to a different color here. Maybe invisible it a little bit. All right, so look at where those are now. If I translate by translating triangle ABC, 6 units left and 3 units up, and then dot, dot, dot. Okay, so what's next here is, so that A and D are the center of dilation, or on the same point. On the same point, I can dilate from A/D, from that center, with a scale factor of. So from here, let's take a look at what that scale factor is going to be. From here to here, how far down and over and stuff do we have to go? So this is down 1, 2, 3, 4, 5, 6, and over 1, 2, 3, or this is down 2 over 1. That seems to be a scale factor of 1/3, because instead of down 6, it's down 2. Instead of left 3, it's left 1. So scale factor of 1/3. And we have to make sure that everything else agrees. Clearly A is on D, so we have to make sure C works the same way. These points weren't perfect, by the way. This would be down 1, 2, 3, 4, 5, 6, and left 6. This is down 2 and left 2. So yes, this thing seems to apply with that that dilation there. That's the proper transformation on that. And once again, it's just based off what we know on dilations, right? That's that big part in that talking point. And that's where I'm going to move forward, right? So yes, these are similar. So determine whether it's similar. Yes, these are similar. The basic thing that they said is objects are similar if you can apply a series of transformations, from one to the other, and that dilations are involved. That you have a scale factor that you can apply to that thing. Because even though I say dilations have a center, if I have to do a translation or reflection or something because it's a different place in space, then so be it. We'll apply multiple things of them because that's how they appear. So hopefully that one made sense. All right, number 10. Number 10, we have Q. So we have a quadrilateral. We have Q at -1, 0. R at -2, 2. S at 1, 3. And T at 2, 1. So it looks like probably like a rectanglish. Not exactly, but, parallelogram. Q, R, S, T. Let's see what this next one's going to be after, because I have no idea. Ooh, it's pretty fat. Such a small object. Thought I learned the way these things snap always, and it seems to be just based on where it is in space. That should have looked better. I think it's supposed to be a parallelogram, but let's deal with it. W. Did I draw all these before? I guess so. W is at 0, 2. X is at 4, 4. Now, I'm curious, because I don't know. I'm curious if it's not a transformation, how I say that it's not. And Z is at 2, -4. W, X, Y, Z. Okay, now, I would not immediately discount this thing as not a transformation. In fact, it probably is. I don't know for certain, but don't look at these things and say, no, they're not similar. They absolutely could be, right? Because it's all going to be based off of certain things that you can do with them. And the first thing that springs to mind for me is rotation. When I'm looking at these, I need to figure out what would correspond. When I look at lengths and comparisons, I look at things like a slope, right? From R to S is up 1 over 3, up 1 over 3. From W to X is up 2 over 4. So up 2 over 4, that doesn't correspond. This is a slope of 1/3. That's a slope of 2/4 is 1/2. Those don't correspond. But when I look at X and Y, from X to Y is right 2 down 6, which it's not the same slope, but if I rotated this thing over, they'd be the same slope. If this up 1 was right 1 and this right 3 was down 3, it would correspond. And then same with this left 1, up 2, and up 2, right 4. They would correspond if they went the same direction. So something I'm looking at here looks like a rotation to me. If I could take this and flip it over in a way. And, like I said, we're probably going to rotate about the origin here. But if I do a 90-degree clockwise rotation here, now, again, it's one of these intuitions that probably, it might not fall on you so quickly. That's kind of why I'm here for this. Now, this R prime would go over here from -2, 2 to 2, 2. It's one of those things you can, take your paper for yourself and rotate it and see where it would go. But here's the R prime. S would go from 1, 3 to 3, -1. Here would be S. T is at 2, 1. Now we go to 1, -2 for T prime. And Q is at -1, 0. We go to 0, 1. There's Q prime. So that would be a rotation here. Now take a look at this one. And obviously it's a smaller figure than the other. But take a look at this one and compare it now to green. Don't think of the blue. Ignore the blue right now. Now look at these things. Look at how R prime is like X. They're together. S prime with Y, T prime with Z, Q prime with W prime, especially if Q prime with W prime. They're both on the Y axis together. This was just general happenstance. I haven't seen this problem before. But now that we take a look at it, looks like we got to double that. Can we double that for these? T is at 1, -2. Z is at 2, -4. S, is everything doubled? 3, -1, 6, -2. 2, 2, 4, 4. Yes. So again, just looking at those doubling effects and how those slope things work, and parallel lines. Parallel lines, right? That's another part about similarity or dilations, that you'd have parallel lines. And dilate from origin with a scale factor of 2. So it's one of these things that I don't know how well I'm teaching that other than discussing it. It comes from knowing transformations pretty well. And that's what I'm getting with it. When I say and, by the way, I mean like and then. Then do this. Maybe I should say then. It's all right. If you say and, you're good. Just make sure you know that doing one versus the other, it might not always work out in the same way, especially if you're doing a translation. All right, number 11. I didn't even finish half the problems. This will go. This might go a little bit. GHI. At least we know it's a right triangle, so this can help us identify where some things are going to be if a rotation's involved. Maybe they hit a reflection this time. I don't know. Maybe it's not a transformation. So here's GHI. JKL to the coconut tree. Chicka chicka boom boom. Here we go. 6, -2. 6, -2. And 1, -2. Okay. J, K, and L. Now this intrigues me. I mentioned this before. There's more than one way to answer it. If so. But, and let me make sure I plotted those right, because I didn't. K is at 6, -2. That's not right. Hold on. 6, -2. Let me make sure I did this correctly before I move forward. J, K, L, G, H, I. Okay. When it comes to dilations, because here's what we can acknowledge. They're both right triangles. Are they similar right triangles? Do they have a proper scale factor, a similarity ratio? I don't know. We'll see. Like from G to H, they're 6 apart. From L to K, they're 5 apart. Interesting. I have to triple, quadruple check everything's right, and it looks good. J to K, that's 6. From H to I is 3 apart. From J to L is 2 apart. When it comes to correspondence, before I even attempt, which I could, there are a lot of ways I could go about this. There's clearly a rotation to be had. But are they similar? Well, these have to share that ratio. There needs to be a proper scale factor that's applied, if so. And making sure I triple checking and plotted all the points correctly, I'm not seeing that scale factor. Now, my description would kind of be far in the reaches, but you can see that from G to H, that should, if I rotated this thing over, if I, flipped it over here, now it looks like that. Now suddenly G is here and H is here. Like that, H would go to L, G would go to K, and 6 to 5 is not the same thing as 3 to 2. 6 over 5 don't equal 3 over 2. They're not the same. If this was 6 over 4, yeah, and we could probably work this thing out the right way. That's why I keep double checking this to say if they want me to get a proper answer, I need to work that out better, but it's not. If J was at 2, 0, it actually probably would work out. Excuse me. But due to, and this is probably not helpful because I didn't do any transformations yet, but due to no proper dilation that can be applied, there are no necessary transformations to be made. I don't know if that's the best way to say it. And therefore, these are not similar. It's okay for them to not be similar. I'm just hoping that it's okay if what I explained works out. Now, this is something, like I said, we'll be doing a lot more of. I don't know if you're going to test whether things are similar, but that's a proof part of a proof of similarity in the future. Scale factors, right? You need a scale factor for it. All right, number 12. Another quadrilateral on number 12. We have D. Oh, let's do blue. E. F. G. Looks like a trapezoid. Oh, yeah. Some form of a trapezoid. Oh, that didn't budge. Now it budges a little. D. E, F, G. Okay. Trapezoidal. Wouldn't mind having a proper similarity one again. 1, -1. L, M. 3, P, 1, -3. Once again, this don't look right. I'm wondering if that other one, maybe there was a typo in what they put, because I really was hoping that one would be a transformation. It just seems weird that it's not. But anyway, scale factor is different. So scale factor is different, than it is what it is. This one's looking a little bit of that same thing, right? So let's connect these, then let's talk. Similar figures, different size, same shape. Just because these are trapezoids don't make them the same shape, right? They need to correspond. I see a sense of correspondence in this area with this area. Problem is, if this part corresponds to this part, these angles are not the same. And I'm not just going by angles. I'm really talking about the whole object in and of itself. This is 2. This is 2. So 2 and 2, and this is 2, this is 2. No change in scale factor. These figures should, I guess, be congruent for all intents and purposes. But suddenly this is 3, and this is 5. Scale factor's changed. Our scale factor is not consistent. No, not similar, as there is not a consistent scale factor. So there's like a 1-to-1 versus 3-to-5. For example, it's been a long day. Versus 3-to-5, for example. And yeah, again, things can be similar and be congruent at the same time. And that's what these things would have been. But this thing would have had to have grown in size. Would have had to have been taller at the same time as anything else. And it didn't seem to do that. All right, that's number 12. Let's keep going. Let's look at numbers 13 and 14. Prove the figures are similar. Okay, if you caught me in the lecture portion of what we were doing, they spoke a mouthful. And I don't feel equipped or willing to speak the same mouthful, guys. I'm going to say it up front. I will try and speak on how they speak in terms of this stuff to the best of what I can say. But from there, I'm going to ask that you write your own thing or follow a template from what your teachers would provide for you. This one's not something I'm going to bother speaking on with my own students in that kind of way. It's very descriptive. It would require a lot of symbols, more than general paragraph proofs that I would have. And I'd probably write some things a little more incorrectly than I can say out loud. That being said, I'm kind of doing a layer here so I can tell you what I'm going to do with this layer. Okay. We are proving, sorry, I'm getting it ready. That's what I'm trying to do. We are proving, actually I don't want that one. That this right that the two triangles are similar. Now, we know they're both right isosceles triangles, and that's marked, by the way. We have a right angle and the isosceles parts by showing they're both the same length. We have a length J here and a length K here, and we have parallel parts AC and RT. So here's the kind of stuff that they mention, okay? I'll say it like this. And I could kind of probably write some of these down, but hear me out as I say them. I'm going to translate this object, this triangle, ABC. I'm going to translate it to the right over here so that A goes with R. Where A was, it's now with R. Yeah? Okay. This thing needs to reflect, right? It needs to have a reflection over a line. When we reflect, it's over a line. Here's going to be my line of symmetry, y'all. The same line that SR is on. Let's reflect across line SR so that what was green here, and this one I have to kind of reflect and then move it. I'm going to flip it over, boom, and pretend like it now went over there. I'm reflecting it over that line, SR. So that A is still on R, but now these things are in line. And with them being in line, because AC and RT are parallel, parallel lines can be mapped on top of each other in that way. So AC, or A prime C prime, whatever it's called now, is now on that same thing as RT. And because they're both right triangles, angle R and angle A are congruent. That makes this AB line up and be parallel with, be on the line with RS. AB is now with RS. Now it's all about this dilation and this growth. This has a length of J, this has a length of K. Our similarity ratio, our scale factor, I'll write this out. Scale factor is going to be through a dilation by dividing K by J. It's weird, normally we say our scale factor is K, but our scale factor is K over J. This is what we have to multiply everything by. So that when we take the length of J, J times K over J, we get K, and that's now how big that this thing will be. And this thing will also grow in that same length because the triangle's isosceles. So when I grow this, boom, and this is just with my computer tool. When I grow this, boom, they can map right onto each other so that not only are those lengths the same, but now C prime is with T, B prime is with S, and A still, by the way, we're dilating from point A prime slash R, from point R. Dilating from point R, that is our center. And it stays on there because any point that's on that center of dilation will stay on there. So because I could do a mapping through translation, reflection, or, and I also could have reflected right here in the middle. Just reflect across there. But I translated first. Translation, reflection, and then dilation. Yes, triangle ABC is similar to triangle RST. So I'll write that triangle ABC is similar to triangle RST. You can see why writing that is not really good for anybody. I don't know how I'm going to have you write all that stuff out, but hear what I said, make use of it. We could have we could have gone off with a single reflection across this line, and it would have applied. So before I did the dilation portion, let's say that this was, the same thing. It would have reflected right across there, and you can see how the green goes with that, and that's fine. You don't have to translate to that part first if you don't want to. But this is how I did it. All right, let's go to the next one, number 14, and hopefully it's kind of the last of these. It says 13 and 14. So number 14, prove, oh, by the way, let me check one thing, ABCRST. Okay, so the other thing, because they might do it here, JKLMQRST. No, it's fine. I was going to say letter order matters. So if they wanted me to, says prove JKLM is similar to QRST, what if it said JKLM is similar to ST, QR, then I'd have to probably do a rotation over here, something like that. It doesn't look like I have to. But let's copy and paste it. Now you have information here, which is pretty similar-esque, probably even easier that we can work off of. Let me make one of these here. Sorry, I'm trying to do a rectangle. Give me one moment. Okay. All right, let's work this thing out. Let's translate this object so that J is mapped onto Q. Translate so that J is mapped onto Q. No, actually, let's go so that L is onto S. Only reason I do that is because where they list our lengths. Notice where they show the X and the Y and the 2X and the 2Y. Let's just put them there because then we have lengths that we can actually talk about. L is onto S, and they called these rectangles. With rectangles, you have right angles. All right angles here. They didn't mention anything on parallel. I think we're good there. LM is on the same line as ST, therefore, with the right angles congruent and the parallel aspects, and then LK is on SR, or I think they just call it S now, just ignore the L. Our scale factor is 2. We go from x to 2x and y to 2y. The scale factor is 2. So we're going to double all of our lengths so that it then becomes this guy right here. And in doubling the lengths, m grows to t, k grows to r, and j grows twice as far out and twice as far up to q. And we're growing from center S. We're growing from center S. And that makes them similar. That was not great description, but rectangle J, K, L, M is similar to, that's the symbol, rectangle Q, R, S, T. Okay. I wasn't great with those problems, but hopefully they kind of work themselves out. Okay, number 15. Modeling with mathematics. Determine whether the regular size stop sign and the stop sign sticker are similar. Use transformations to explain your reasoning. Well, I'm going to describe some stuff first. First of all, yes. Yes, they are. Yes, they are similar. They have the same shape, regular octagon. Now, that's important. But their size changes. The scale factor, well, this is where I'm going to start to do some other stuff. This is why they're similar. Okay. Now, as far as transformations go, you can translate this thing. Okay, I guess I do still have to describe it. It's actually literally things. Translate. Well, they say regular size stop sign. I thought they said regular polygon, but they're both regular octagons. That's what a stop sign is. Translate regular sized stop sign onto sticker at the corner, at the top left corner. That's hard to say because there are two top left corners. I mean this one right here. Top left corner marked. Then dilate with scale factor of 4 over 12.6. So they're both inches. I don't know what that is. It's the same as 40 over 126, which is 20 over 63. I don't know. I'm just trying to make sure that it's integers only when I do that. So 20 over 63. So it's a reduction. I don't know. Oh, from that center. From marked center. Okay. Yeah, so, some of these description things are really hard to say. All right, error analysis. Describe and correct the error in comparing figures. Let's see what they talk about here. Number 16. Whoops. Okay. From figure A is similar to figure B. Well, because they said correct the error, I'm going to guess that's not the case. Let's see if we can determine something that breaks it. Let's start by looking at lengths because we seem to see what would orient, right? That's a length of 4, that's a length of 2. So for all intents and purposes, this would have a scale factor from A to B of 1/2 if everything else falls in line. This distance here, however, is 6, and this distance here is 4. So that's a different scale factor. That's not a scale factor of 1/2. They say figure A is similar to figure B. When it's just not true. Say figure A is similar to figure B. However, there are different scale factors applied in the object, such as 2 over 4 equals 1/2 and 4 over 6, or 2/3. And 1/2 is not 2/3. So that's kind of going on. So figure A is not similar to figure B. Okay, so that's one where it's... they say correct the error. I'm correcting the error. They said similar, and it's not. So I can't really say anything else. I could say if A looks like this, but that's not what it is. Okay, number 17. Making an argument. A member of the homecoming decorating committee gives a printing company a banner that is 3 inches by 14 inches to enlarge. The committee member claims the banner she receives is distorted. Do you think the printing company distorted the image she gave it? Explain. So I'll say right now that without them saying the phrase similarity ratio, we're doing a lot of similarity ratios where we are comparing to see if proportions align. When they say 3 inches by 14 inches for one of the things, we're really comparing how this 3 inches to 14 inches compares to this banner here, which has 18 inches by 84 inches. And did everything grow by the same amount? So I need to figure out 3 times what gives me 18. Does 14 by that same number give me 84? It's really what I'm looking at. So is K the same for these? When I do 18 over 3, and by the way, these are all inches. Inches over inches, and 84 over 14. Yes, that'll give you 6. That's a scale factor of 6. They are in agreement with each other. They all work out. Your committee member is wrong. I mean, I don't know what else is distorted or not, but your committee member is incorrect. This is a proper proportionality. The printing company did not distort the image as the dimensions apply a consistent scale factor of 6. There we go. I don't like I don't like where that 6 is. There we go. All right. That's fine. Okay, that's number 17. Number 18, 5 more problems. Determine whether each pair of figures is similar. Explain your reasoning. Well, it's going to be one of those things. I'm not going to be mapping transformations if they don't ask me to. But it's all about size and shape. If I can translate things in a certain way, then everything would work out. Now, when we look at the suns, let's make sure that the shape things are the same. We got 1, 2, 3, 4, 5, 6, 7, 8 of these, and 1, 2, 3, 4, 5, 6, 7, 8 of these. Top to bottom, looks like the shape is pretty identical. Looks like one's a dilation of the other. Looking pretty good on A. Yes. Same size, different shape. That's all I'm going to say. You can translate it and dilate it. Now, there is a possibility that we would have had to rotate something, but I'm looking for something to be skewed, and it doesn't look to be skewed. Whereas here in the heart, you can clearly see a difference, and I'm trying to decide what that difference is. Looks like maybe the height's the same. If I measure that one up and compare it, oh, look at that height. Looks like the same-ish height. But then it's stretched clearly. We compare widths. Okay, if this is the width here, got a little bigger there, right? So not quite the same width. So remember, you have to grow every dimension the same amount, and that's not the case of the heart there. So no. They're both hearts. That doesn't mean they're the same shape. Excuse me. I said same size, different shape here. I meant same shape, different size. Same shape, different size. But over here on this next one, no, different shape. Different shape as in different size. Skewed, same height, different width. Basically no consistent scale factor. No dilation occurring there. All right, here we go. Number 19. Graph a polygon. Oh, my eyes. Graph a polygon in a coordinate plane. Use a similarity transformation involving dilation, where k is a whole number, and a translation to graph a second polygon. Then describe a similarity transformation that maps the second polygon onto the first. Oh, onto the first. Oh, what? Oh, okay. So open-ended, I guess. I'm going to do a triangle. Keep it basic. Let's go. Let's go A, B, C. Let's dilate it. Wait, use this on a translation value. Dilation and a translation. Let's dilate it by a scale factor of 3. So I'm going to triple everything. Actually, can I fit 4? Let's do 4. So 4 times bigger. So B is going to be at, or B prime is going to be at 8, 0. C is going to be at, 4, 8. C prime. And A prime is going to be at -4, -4. Okay. So there's the first part. Then let's do a translation. And I'm going to describe these. Don't worry. I just want to kind of do them first. Then we'll go backwards. They said go to the other way. So there's that dilation. It's from the origin, by the way. And then let's do a translation. Let's go 6 units left and 2 units up. No, let's go 4 units left, 2 units up. I don't want to override. I don't want to go right over anything. So 1, 2, 3, 4 units left and 2 units up. B double prime. 1, 2, 3, 4, 1, 2. And 1, 2, 3, 4, 1, 2. Great. Okay. So my original set that I had, with all that in mind, I had A at -1, -1. B, see, I could be a textbook maker, at 2, 0. And C at 1, 2. Then I dilate from origin with scale factor of 4. And then I translated 4 units up, or left, and 2 units up. Now, they also have those rule things, right? I could have done the from X, Y to all that kind of stuff, and I didn't really do that. Now they said, describe a similarity transformation that maps the second polygon onto the first. So now going backwards, we literally do everything backwards from here. So the answer to this thing is take A double prime, B double prime, C double prime, that figure, and translate 2 units down. It doesn't matter if I say down or right first. And 4 units right to get back to that spot. Then dilate from origin with scale factor of 1/4 instead of 1/2. So it goes the opposite direction with everything that you do, which is kind of a pretty good way of talking about that. And no, I can't do the dilation first, and you can do that dilation and a different translation, but you got to account for the fact that everything's dilated down now before you do that. All right, number 20 is the composition of a rotation and dilation commutative. I was talking about this earlier. Is the composition of rotation and dilation commutative? In other words, do you obtain the same image regardless of the order in which you perform transformations? Justify your answer. Now, it's interesting to ask about rotation and dilation and not about translation and dilation. I really thought they would have done it, at least especially because there is a solid answer to that, and we just did a problem number 19 that spoke on it, and they didn't do that. It says justify your answer. My justification is in multiplication. Rotations, this depends if you're dilating from the origin and rotating from the origin, by the way. If you're rotating and dilating from the origin, then yes. This is because every result is from a product of some sort. And products, multiplication is commutative. You can change the order of the multiplication. It doesn't change. Do something times 2 and then times 3 versus times 3 and times 2. Things like that. Those are fine. However, if it's any point in space or on a graph, then no. However, if it is from distinct points in space, then no. This is just because of what you're doing something with. I always like to take something like, let's just take the letter F and do something with it. Let's have a distinct place where we're going to do a rotation and a dilation. I want to rotate here. And then I will dilate well, I'll dilate here. I don't know if any of this is going to work right. If I do the rotation first, then let's say it's a 90-degree rotation, then I would, the rotation would look like that. The dilation from there is going to grow out from here, and it's going to go out this direction. So like that, and it's going to expand, and it goes out that direction. Let's say it was like times 3, then it would look like this, an F going downward like that, right? Hold on. I'm kind of running out of room on my bottom. So it would go like that. What does this F look like? Like that. Whereas if I did the dilation first, then it would expand out. Well, no, because check out this rotation. The rotation's there. And then now when I rotate here, it's now going to take it from upon this to get that rotation in. So no, it wouldn't. It's just the different points in space that would change what it is you do with it and where, because the points and where they are. If they're both from the origin, heck, if they're both from the same place, I don't want to make stuff up. I think they need to be from the same place. Otherwise, I don't know if I'm answering that well enough. But that's kind of where I'm going with that. If it was the translation question, it would be a lot better to talk about and justify and say that no, you couldn't do it from translations versus rotations. But otherwise, from an origin on a graph, yeah, it does work. So it just depends on what you're doing it from, honestly. It just depends. I think they can just be the same. I don't think it's origin. I think it's from the same place. Same place. So then yes. And I said because multiplication is commutative. It's multiplication and it's commutative. It is commutative. From different distinct points in space, then no. Okay, 2 more questions. Number 21. Looks like no proofs. Actually, I can't tell if these are proofs or not. Number 21. Quadrilateral JKLM is mapped to quadrilateral J prime using the dilation here. Then that's mapped to here using this translation. The vertices of this are here. Find the coordinates of the vertices of the original. Oh, that's the primes that we're given. So we're kind of in the middle part here. Are they similar? Explain. They better be similar. Because you just told me what transformations to do. The problem is the points they gave me. Okay, I'm not going to use a graph. I don't think there's a reason I need to use a graph. So J prime, let's do this. J prime is from -12, 0. K prime is from -12, 18. L prime is from -6, 18. M prime is from -6, 0. Let's figure out where these other points are, because this is kind of the middle. Let's figure out what happens to get to the double primes and where we came from to get to the primes themselves. Okay, so for J, K, L, M, and for J prime or J double prime, K double prime, L double prime, M double prime. Now, are they similar? I think they're supposed to be. I think there's, yeah, because we applied transformations. So the first set goes from some XY to some 3/2 X, 3/2 Y. So to go backwards, that means we got to go 2/3 reciprocal, right? We're multiplying by 1.5 here. We divide by 1.5 here. So 2/3 of those things, let's write those ones out. This would be -8, 0, and -8, 12, and negative 4, 12, and negative 4, 0. Those are the original points. Then there's a translation that goes on from the primes to here, where it says x plus 3, y minus 4. And this is why I said we really don't need the graph stuff here. We can just calculate all these. They gave us the points. So negative 12 plus 3, 0 minus 4. Negative 12 plus 3, 18 minus 4. Negative 6 plus 3, 18 minus 4. Negative 6 plus 3, 0 minus 4. You know, like that. Are the quadrilaterals similar? Explain. Now, I don't know if they mean on a graphing basis. I could tell you in some other ways by looking at these things on how they probably would be as well. Because, like, they look like they're even rectangles, I think. Because these are the same widths and these are the same heights and things like that. So I'd assume so in that regard. But yes, because a series of yes, JKLM is similar to J double prime, K double prime, L double prime, M double prime, because a composition of transformations was applied to get from one to the other. Is that all we need to find the coordinates? Yeah. Okay, that looks good. Not a proof. And then number 22. Repeated reasoning. Use the diagram. Connect the midpoints of the sides to make another triangle. Is this triangle similar? Use transformation to repeat part A for two other triangles. Wow, that's a lot. 2 of my own or 2 within this triangle? I assume 2 of my own, because otherwise these would get pretty, yeah, that would get pretty small. So let's get the midpoints. I'm not going big into midpoint formula or anything like that. This is a midpoint here. 1, 2, 3, 4, 5, 6. This is a midpoint here, and halfway right there we got this guy. So we got some midpoints. If I called them T, U, V. Now, one interesting bit that we make this triangle here is we can see we clearly have another right triangle within. So right angle here, and here's a right angle. Now they're asking if they're similar. We're going to learn more about triangle similarity in the future, but I can start to tell you some things that we want to look for in the case of this. Obviously, they're going to ask us to talk about transformations, but we start looking at, again, same right angle there. So that's a good first step. And then other things like things that would correspond. This clearly appears to be a rotation of this other one. So like this part being 2 corresponds to this part, which is 4. Looks like it shrunk half the size. And this part 3 corresponds to this part 6, which is half the size. And that makes sense, they're half the size. They were midpoints. So yeah, it's taking on this similarity aspect of this thing. So use transformations to support your answer. This can be a rotation, right? I can take this triangle here, and I can rotate it. I can even rotate it around this midpoint, this U. Rotate. Well, how do I best want to rotate it? Because I have to dilate after, and I need a center. Oh, yeah, I can rotate and dilate from the same place, right? Rotate from U, the new point U, 180 degrees. Whoops. Or rotate 180 degrees from U, the new point. I did it again. Then dilate. And I could have dilated first with scale factor of 1/2 and center U. So everything's going to shrink into there. This thing flips over. It flips over so that it ends up looking, I'm going to do it in red. So it ends up looking like this right here. Now Q is actually, here's what it actually looks like now. Now Q is here, or Q prime. R prime is actually here, and S prime is here with that rotation, with that as its center. Flips over. And then we shrink. Oh, I'm sorry. U would not be the center. U would not be the center we dilate into. This thing actually shrinks into, oh, the old Q point. So center of Q. You know, maybe I should have shrunk with Q first. Center of Q. Good thing I drew that. Okay, repeat it 2 more times. No. You can do it 2 more times. I'll do it 1 more time. I'll use this purple triangle I have right here. Let's see how the purple one works out. I think that looks like a midpoint. That looks like a midpoint. That looks like a midpoint. And look at what we have here, that same-ish in that same way. Look, there's another rotation. It goes 180 degrees flipped over, and then that happens. Now, why is this happening? Let's talk about why it's happening. Think of what we're doing with these. We're making mid-segments. What do we know about mid-segments? What we know about mid-segments is a mid-segment is half the length of that third side and parallel to that third side. You're finding parts that correspond, and they are half the size. They shrink by those scale factors. They're parallel and half those lengths. I mean, that's as deep as I'm going to get into it, but you can do it with 2 others for yourself, right? I'm kind of spent, and I've taken care of that. So what conjecture can I make? They didn't ask me to explain why. The inner triangle is always similar to the bigger triangle with, and I'm not saying where the center is, but with a 180 degree rotation and a 1/2 scale factor dilation. This is due to the mid-segment theorem, triangle mid-segment theorem. It literally refers to things regarding parallel lines and half the lengths, and I think that's going to work itself out. All right, guys. That's for triangles, though. They didn't say it for any other things. They said triangles. All right, guys. That's going to be it for me. That ought to do it for this one. This is Mr. Robbins. Thank you so much for watching. Kind of a different section, and it's really an exploration one, and one that tests your ability to know things from before and describe things and work things out in the way you best can. Hopefully 8.3 will have a new change and challenge in what you're learning and what you're doing, and I can understand where this can still kind of jumble you a little bit, as it did me to explain it to you. Thanks so much for watching. Check the timestamps down below if you need to see anything again, and take care. I will see you in the next one.